Hello everyone, welcome back to Tech Simplified, and today we are going to dive into the topic rate limiting in distributed systems. So it is a very crucial topic in system design, and let's get started. So first we will see what is rate limiting. Simply put, it is a defensive mechanism that controls the rate of requests a client can make to your service over a given period of time. Okay, so let us say this is our server and we have clients here who are making requests to our server. So in this scenario, we need a way to control the number of requests a client sends to us. So if the same client sends multiple requests, then the server might become overloaded, right? So because of this, we need some mechanism to control the behavior. So why do we need rate limiting? First thing is to provide stability to our system. Okay, it prevents a single user from overwhelming our servers. Second factor is for fairness, because we want every client 1, 2 and 3 to be able to access the server and its resources in a fair and equal manner. We don't want one client bombarding the server with multiple requests and the other clients waiting. That's not what we want. And the third thing is for security. Why security? Because it helps to mitigate scenarios where one client can bombard our server with API abuse or denial of service attack. And to secure our server from all these things, we want to implement the mechanism for rate limit. So implementing this on a single server seems to be straightforward. Basically what we can do is we can maintain a count of requests that are coming in for one client. Okay, let's say for per client we maintain a count of 100, and whenever the number of requests from client 1 exceed 100, we stop the client 1 from accessing our server further. So at the single server level it is doable, but then we have the distributed challenge. For a single server, the implementation is simple. Basically for a given user or an IP address, let's say we have a user who is bombarding our server with multiple requests. It can be a user or an IP address. So what we can do is we can create or maintain a count for this user and stop it. As the request comes in, we basically check the counter, increment it and process the request. And if the counter hits the limit, let's say 100 per minute, then we block the rest of the requests for that minute. This works great for a small application, but modern applications are distributed, right? We have multiple servers which are often behind a load balancer, and that's where the single counter approach breaks down. Because if every server has a count of 100 and so on, then per minute we end up serving 700 requests, and that is not what we want to be doing. This problem is known as inconsistency. The global limit is inconsistent with the sum of the local limits. Let's say we have the global limit of 100, but the sum of the local limits is S1 plus S2 plus S3 till S7, that is 700, which is not equal to 100, and it contradicts. So this is the problem of inconsistency in counts in a distributed system. Now let us see what the next problem is. So let's say we have a server S1, we have two clients C1 and C2, and they are making a request here, and both these requests arrive at time T1, and at time T1 the local count of S1 is 99. So at this point of time both C1 and C2 try to increment this count, okay, and this results in a race condition. So this major issue is known as the issue of race condition, where both the requests try to increment the counter, effectively resulting in 101 requests, which is not what we want because our limit is 100 requests. So clearly from these problems, the solution that comes out of it is we want our counter to be centralized so that all the servers have a common view of it. We also want our counter to be atomic in nature. Okay, basically we want only one transaction can increment it. So these are the two things that we are looking in our solution, correct? We want a centralized and an atomic counter. So luckily we have a solution in this case, and the solution that we want to implement here is of a centralized store. The industry standard solution is to move the rate limiting logic to a central, highly available and fast data store, typically a distributed Redis cache. So this Redis acts as our centralized data store, and to this data store all our servers can talk and get the latest value of the global counter that we are trying to implement. When a request comes in from a client, all the individual servers now don't maintain the local counter with themselves. They make an API call to our centralized Redis, and this gives back the latest value of the count, and then based on that count, the client is served the request or it is denied. Redis is perfect because it supports atomic operations like the increment INCR increment operation, and this means the read check and write for the counter happens as a single uninterruptible operation solving the race condition. Now that we have a centralized store in Redis, let's look at the algorithms used to define the actual limits. Let us discuss about the main algorithms that are used for rate limiting in distributed systems. Each algorithm used has its own trade-off and varies based on accuracy, memory, and burst handling. So we will see what these factors mean, and let's look at the first algorithm, that is called fixed window counter. In this algorithm, define a fixed time window, let's say 1 minute, and within this 1 minute we define the count of requests that are allowed within that window, let's say 50 requests. We are effectively saying that in 1 minute we will not be processing more than 50 requests, and at the end of 1 minute the counter is again reset. So let us imagine it via a timeline. So let's say this is our time. We start at 0, 1, 5. These are the minutes. So number of requests allowed during the first minute is 50. Okay. As soon as the time crosses 1 minute, let's say during this first minute we got 3 requests from clients. So the count became 47. But after the minute pass, this 47 will again be reset to 50 for the start of this window, okay, and so on. So this is one of the simplest algorithms, and the gist is at each window, at the end of each window, the counter is reset. Now let us look at what is the challenge of this algorithm. Let us consider this window change timing. Okay, so this is the third minute. Let's say at 2 minutes 58 seconds and at 3 minutes 2 seconds. Let's say we get 45 requests here, and at 3 minutes 2 seconds we get 49 requests here. Now if you sum it up, during the span of these 4 minutes our system is bombarded with 94 requests, and that is not what we want. We want our system across all the time intervals so that we maintain the core ideas of stability, fairness, and security. So this problem is known as the boundary problem, because at the boundary there is a possibility of burst of requests. To solve this problem, we will take a look at the second algorithm, that is the sliding log algorithm. This is the most accurate algorithm for rate limiting. What we do here is, for every request we record a timestamp in a log, usually stored in a Redis sorted set. Okay, so we store the timestamp in a log file or in a log data, and this is stored in a Redis sorted set or a cache, you can say. So to check the limit, you can count all the timestamps that fall within the last window, say the last 60 seconds. So let us look at this algorithm on the timeline. So what we do here is, let's say this is our timeline and we have minutes marked here. For every part of this timeline, what we try to do is we try to maintain a log here. Okay, and inside this log, let's say this starts at 30 seconds and it goes till 1 minute 30 seconds, and during this 1 minute window, what were the requests, how many requests were made and at which time. So let's say at 0.05 we got one request here, at 10 seconds we got another request here, so it is 1, 2 and 3 here. Okay, so we'll write at 5, 10 and 50. On this side of 1 we get, let's say, at 1 minute 2 seconds, 1 minute 12 seconds and 1 minute 33 seconds. So 1 minute 2 seconds, 12 seconds and 33. 33 would go out of the window, so let's make it 23. So this is 23. So we maintain a similar log for every second that passes by. So a similar log file would be seen here, right? Then a similar log file would be seen here, and a similar log file would be seen 1 second later, that is here. Okay, so these are all the sliding window logs. This is the most accurate algorithm, as you might understand, because for every window we are maintaining the exact number of requests that are there. And how this prevents the boundary problem is, at this boundary we know that from the previous section how many requests are there, and from the next section how many requests can be accommodated. So this algorithm solves the boundary problem very effectively. But for a high limit, let's say the request per minute limit is quite high for our use case, let's say it is 10,000. So what we will end up doing is, in this log window we will end up storing 10,000 values of timestamp. Okay, so we are storing and checking 10,000 timestamps for every incoming request, and hence it becomes memory intensive, which is the main drawback of this algorithm. So here the trade-off we are making is, we are trading off memory and we are getting high accuracy here, and also it is computationally expensive to store and look up so many timestamp values under huge load. So this is the sliding log algorithm. Let us look at the next rate limiting algorithm, called the sliding window counter. So this algorithm is a popular and practical method for rate limiting in distributed systems. It is considered a hybrid approach aiming to provide the smoothness of the sliding log, okay, and while maintaining the low memory footprint and the speed of the fixed window counter. So this is widely used across the industry. Okay, the core idea of this algorithm is weighted averages. So the idea is to calculate a weighted average of requests across the current and previous fixed size time windows to approximate a true sliding window. Let us look at how this algorithm works. Okay, let's consider a window size W, and let's consider our limit on the number of requests to be L. For our example, let's consider the window size to be 60 seconds, and let's say we will allow 100 requests inside this 60 seconds. Now the calculation or the sliding part. How we do it is, we first identify the window, or we determine the current window and the previous window. So let's draw a timeline here. This is our timeline, and we have marked the minutes 0, 1, 2 across 5. Let us consider a window like this, and this window starts at 45 seconds and it goes through up till 1 minute 20 seconds. So this is, let's say, 20 and this is 45. Okay, so how the calculation part of it works is, first we identify the window, and this is our identified window. Then we find the time elapsed. Basically, this is the fraction of time that has passed in the current window. For our case, this is this much of time, that is 20. Now we get the count, or we fetch the request count for the current window and for the previous window. So we get how many requests are made during this 20 seconds, and we also see how many requests were made during this portion of the window, that is from 45 seconds to 1 minute, that is during this 15 seconds. So let's say 2 requests were. So for our example, let's assume we already took the limit to be 100 and our window size is 60 seconds, and let's say in the previous window, that is from 0 to 1 minute, we had a total of 80 requests. So this is the previous one, and let's say in the current one, that is in the current window, that is from 1 to 2 minutes, we have received 40 requests till now. By till now, I mean till 20 seconds have passed. And the new request was made at 1 minute 20 seconds, as we saw here. So the time elapsed in the current window is how much? 20 seconds, which is this. Now what is the fraction of the previous window remaining here? In the current window, we have taken 20 seconds. Our total window size is 60 seconds. Fraction remaining from the previous window is our window size of 60 minus current what we have passed, so that becomes 40. So this 40 seconds weighted average we have to calculate now. So what is the weighted average of 40 seconds? 40 by 60, which is 0.66. So this is the weight we apply to the previous window's count. So now what will be the weight calculation in our case? So we take 0.66 weight of the previous window plus all the requests that we have received till now. So this turns out to be 53 plus 40, which is 93 requests. This comes out to be 93 requests. Now as this number 93 is well within our range of 100 requests per window, so in this case our request is allowed and processed. In case this number was something more than 100 or equal to 100, the request would be dropped. So if we try to plot the rate limiting of these algorithms as a curve, so fixed window would be something like this, with spikes at window boundaries, and the sliding log smoothens this out, but again has a high memory footprint here, and the sliding window something like this with low memory footprint, as well as lowering the spikes that we found on the fixed window. By using this weighted value, the algorithm prevents the harsh reset spikes of the fixed window, giving us a much smoother rate limiting. To implement this, we use Redis sorted sets, and the Z set stores the request timestamps as the score and the unique request IDs as the value. So let us conclude this video and take a look at the key takeaways here. So to wrap up, implementing rate limiting in a modern distributed system is about promoting stability, fairness, and security in your system. It mainly involves solving two challenges, that is inconsistency and the race problem. Okay. The solution to this problem is implementing a centralized and a highly available key value store like Redis, which can be used to maintain global counts. We leverage the atomic operations of Redis to maintain a single consistent global count. And when choosing the algorithm, the sliding window counter offers the best balance of accuracy, memory efficiency, and smooth traffic management. If you found this explanation helpful, please give the video a like and subscribe for more deep dives into system design. Thank you for watching, and I'll see you in the next video.